So a long solenoid of radius r has n turns of wire per unit length and carries a time-varying current that varies sinusoidally as I of t is equal to I max cosine omega times time, where I max is the maximum current and omega is the angular frequency of that oscillation. So determine the magnetic field of the induced electric field outside a distance r is greater than the radius from the long central axis. So when you hear induced electric field and you're working with a solenoid, right, that's having a changing current, you know it's going to be a Faraday's law problem. Changing magnetic field is resulting in an induced EMF, and an EMF is just the line integral of the electric field, right? So it's a line integral, and when we're choosing our path of integration, we want to use symmetry. So for something circular like a solenoid, you can imagine that, yeah, the induced EMF will be kind of like, or the induced electric field really will kind of wrap around the solid. And this is I know this is a really bad picture. These like little band thingies, they're meant to be turns of wire, but the actual path of integration will be a circle, because you can imagine that at every point along that circle, it's equidistant from the central axis, so it's going to have the same electric field. So so Faraday's law, right? Integral E dot ds is going to equal the change in flux per time, right? So as a quick let's not get there yet. You'll see in a second. The electric field, right? It's going to be the constant around that path. So I can pull out the integral, and I really get E times integral ds is going to equal the time derivative of the product BA, right? And obviously, so integral ds, that's just the circumference, right? 2 pi r. Little r, right? Because this is the distance from the center that we're trying to find the electric field at. The area is constant, right? The area, that's not changing. It's just pi big R squared, right? Because, it's big R, right? That's the area. Now, what's really changing is the magnetic field. And just as a reminder, right, this is a refresher part, for a solenoid, you can use Ampere's law to figure out what is the magnetic field at a certain time, right? Because I know that, well, hey, according to Ampere's law, integral b dot ds is going to equal mu naught times I enclosed. So hey, if you imagine a path, I'm going to do it kind of on the central axis, right? If you imagine a path, a rectangular path, I know that the magnetic field will be kind of constant on this path, so I can pull it out of the integral b, and then let's say this is a length, right? Really, the magnetic field actually kind of exists like right on the solenoid, right? So hey, b, the integral of that path, well, there's no magnetic field at this point, it's negligible, so that integral ds, that's just the length, L. And how much current is enclosed? Well, there's this current right here that would be pointing either into the page or out of the page, right? As the current kind of loops around. So I think it would be into the page in this case. So it would be, well, mu naught, it's just whatever the current is, the main current times the number of turns L, N, and you get, dividing by L, you get B naught mu naught I times little n, where little n is the turns per length, right? Because when I divide by L, I get turns per length right here. So that's the little n in the equation. I can just substitute that back into my equation. So I get 2 pi r times E is equal to pi big R squared. Taking the derivative of mu naught. Now, mu naught and n, those are constant, right? So I'm really taking the derivative of time, or current, sorry, yeah. I'm really taking the derivative of current with respect to time. So if I move my work over here, the pi's drop, which I guess is pretty nice, and I get 2r times E is equal to r squared mu naught n times, now the derivative of I, this is like a sinusoidal equation, so the derivative of cosine is negative sine, and then I just pull out the omega using chain rule, right? So I get times, and I'm working with magnitude here, so the negative won't really matter, but I'm just looking at my notes here. The negative won't really matter, but I'll get omega times I max sine omega times time. Right, now I just divide by 2r, and I get my final result. E is going to equal r squared times mu naught times n omega I max all over 2r times sine omega times time. Which is pretty crazy result, but kind of makes sense, right? Because as you get farther and farther away from your solenoid, as that r gets bigger, your E gets smaller. The induced electric field at that point in space is smaller, and I believe this is the right answer. I have the answers right here, just so I'm kind of making sure not teaching the wrong thing. But now, what if we're looking at the r inside the solenoid, right? What if this distance r is within the solenoid? Well, now in this problem, we saw the change in magnetic flux through the total area of the sort of thingamabob, right? Because there's really electric field, there's really magnetic field going through and changing, because the current is changing, right? Changing through the whole area. But now we're looking at a smaller radius in the total r. So if I think about my solenoid, right? Just pretend this is a solenoid. I'm looking at a distance r right here, or little r right there. So I'm only worried about, well, what is the magnetic flux going through that small area? Because that's kind of the area, if I just gotta make sure, yeah, that's kind of like the area where you're getting a chain of magnetic flux for that kind of line integral right there, right? So what we're gonna do, same process, but now I just gotta keep in mind my little r's and big r's, right? So E dot ds is gonna equal d flux dt. Now I'm doing the same thing, but now I'm gonna get my E times 2 pi r. But my area is now just that small portion within the solenoid. So it's gonna be pi little r squared, right? Whatever the radius of whatever that radius of what we're measuring at, right? So, and then I'm still doing dB dt, and that still is essentially the same, right? E times, now I can drop one of the r's and drop the pi, so I just get 2 times E is going to equal r times mu naught times n, which I'm getting just from over here, times di dt. And di dt, well, that's just our omega I max sine I max. Well, that's a movie thing. It's omega times I max times sine omega t. And in the end, I get E is equal to that whole thing. So mu naught n omega I max over 2 times r sine omega t, which I'm pretty sure is the answer. Yeah, that looks about to be the answer. So yeah, hopefully this makes sense. It's just an application of Faraday's law, right? When you're trying to find induced electric field, magnetic fields generate induced electric fields. So it's just an application of Faraday's law in its full form, in its full integral form. So yeah, thank you for watching.